is allows you to quench through the core. So it was the term hardenability that you don't have with a low carbon steel. And therefore, if you want to make a part that through the core is a higher yield strength, you need to specify a chemical designation like this, so it's possible to make it hard all the way through the core, increase the yield strength. But we will see that depending on what you're building, you also will want to say how that hardening is going to take place, hopefully. It depends on the application. So that's today's lecture. And I brought some pieces to circulate. One is just an aluminum bar that has a little bit of machining in the gauge section. Because tied to the material specifications, and this is stainless steel. Can anyone tell me, have you covered stainless steel yet in the welding? Yes or no? No? Not specifically, because there are going to be a few lectures
Mike
specifically.
had talked about it a little bit, yeah.
He did, or you
Yeah,
will?
he did. No,
He did,
has.
okay.
Yeah.
So the reason I'm bringing the stainless steel is these pieces have the chemistry that was specified with 316 stainless steel, which is very common. But it's another example where even if I tell you right from the beginning, yes,
Do you have an extra handout? I want to know.
oh yeah,
Oh,
you should
here's one right
be
here.
by the door. So if I say I have a stainless steel 316, it's a wrought alloy, lots of times I will put L on it. It's not resistant to all corrosive environment, actually has a big limitation with respect to chlorides. If you throw the icing salt on it, you're going to start pinning. So if you have railings and those type of applications, it has very serious limitations. But yet it's not the most widely used stainless steel because it's more expensive than the basic stainless steel, but it's a stainless steel used for architectural applications when a certain level of corrosion resistance is needed. So they used it for the roof on the new convention center, the one that's on Seaport. If you go around the building, they have this big gutter that is, it's not a flat roof. So the roof has this big gutter on the roof. This is about maybe 2-3 feet high. And they have essentially a high smelting system, so they will collect any water on the roof. And it takes a lot of energy, but in terms of aesthetic of the building, you don't have water and icicle running all around. They had when they built this, they had for about 4 miles of gutter all around. The situation is outdoor by the ocean, but they had to decide between aluminum and stainless steel, and for reasons such as weldability and other reasons, they went with that stainless steel alloy. Now, once you make that decision, you still have to worry about whether it's going to be corrosion resistant. That's something you care about. It's not a question of yield strength, hardness, and all those other considerations. So the two pieces I'm circulating are example where people during the installation of the stainless steel were using tools like regular steel that essentially contaminated the surface. And if you have some regular steel on the surface of a stainless steel, now you start forming the rust because it's acting as, you even have differential metals all of a sudden. So all they saying you want to use stainless steel will not necessarily get you home with respect to corrosion resistance. The risk of contamination is one. The other aspect is welding. Welding of stainless steel is very common, but if your shielding gas contains carbon, the carbon is going to pick up the chromiums in the stainless steel and form precipitate, and then all of a sudden, it's not available for corrosion protection. So if you started with, say, in this composition, somewhere around 15–20% chrome, after that chrome reacted with the carbon, it's not available anymore, and you don't meet your 12% minimum requirement. So that's really what I want to emphasize, that material and process specification is very important in terms of achieving your goal. If you only say, I want this alloy, they likely, you just have to assume that they will weld it the way they want to weld it. And then if that means the regular welding process that has a carbon-based shielding gas, you're gonna have a problem, a big problem. It's not so much in the weld pool, because a lot of times you can come in with a filler metal that has so much chrome and nickel that it will be corrosion resistant. What matters is the metal that's in the heat affected zone right next to it. So if I have a fillet weld here, and I just do a single bead, if this T-connection goes through weathering with chlorides, it's possible that my weld here will hold strong because it's got a good chemistry. The metal right next to it here is what needed to be protected during the heating and cooling process in the heat affected zone, and that's where you can have the chrome depletion. So to alleviate this, these details of the welding process and the shielding gas can go a long way. But it's something, if you ever work on a project where you really have to specify what a fabricator will build, it's something you have to tell them explicitly. You can't assume, unless he's got special knowledge of what you're trying to do, you can't assume that he will know that how much you care about that corrosion protection. Plus, he's a contractor. So that's where it goes from specifying the material, and then if it's going to be welded, specifying the process. And you would be surprised that even in the welding code for stainless steel, it's not all inclusive. Yet, if there's something in particular, oh, I'm getting a connection. Yes. If what I'm looking for is a corrosion resistance, I'm supposed to be, as an engineer, I'm supposed to be the best person to know how I'm going to do it. How I'm going to do it is, if I have to heat up this base material, first of all, I want this low carbon. That means low carbon in the base metal, so when it heats up, it doesn't consume those the chromium that's in the alloy. Most stainless steel now, even if I was to buy a 316, will probably come as a 316L, because it's not too much more work to produce the carbon. It's avoiding them to having to carry both. There are no real advantages into not having the L. So even if you buy a 316, it could be a 316L. Is it guaranteed to be 316 low carbon? No. So you still want to put it on, but it's only the chemical part. Now, we're going to talk a little bit more about ASTM, because it's taking us a step forward in terms of specifying the material we want. So if you go to the third page of the handout, I'm talking about ASTM 836.
Mr. Bellemare, do you
Yes.
see the HDMI cable?
He's working to put down. but it may or may not work.
No.
Well.
You got another one?
audio-visual, they're
Maybe
on
you
their
had the
way
better
down.
one.
Well, audio visual's on their way down, so.
Okay.
I'm not sure if these work, but.
Anything will work. If you go
And audio visual's actually on their way down.
locally here and try to buy a big I-beam, it's probably gonna be 836. Because people sell I-beams for buildings, mostly. So they have to meet certain minimum quality requirement. I say minimum because all this says, according to the STM, if you look at table 3, you have a minimum yield strength of 36 KSI. So that's why. And that could be easy for you to remember, it's 836. It's the only one that has this correspondence. Just happened to be, it's a very old standard. It's been updated over time, but when they decided they were gonna do structural steel, they decided, okay, well, the minimum we're gonna ask for is that 36 KSI initial yield strength. If you look into more of the detail, it tells you the tensile strength is going to be between 58 and 80. 58. If you ask me, that's a pretty broad range for today's standard. It's not that hard through the selection of the grain size through the rolling process to control your yield strength within about 5–10%. So when you see that range, it means a lot of time the A36 steel will be a lot stronger than the minimum. But it can't be stronger than the maximum. There is a maximum there for you, and it could be to your advantage. There are applications where you want things to deform. Well, if the yield strength is too hard, too high, it's not going to be possible to deform it. So, personally, I do like to see that there are some maximums here. A lot of steel specification also have maximum hardness in these ASTMs. And some of that is to resist hydrogen embrittlement or hydrogen-induced cracking. There are very specific reasons for putting them on. The structural steel one doesn't. All it says when you run your tensile strength, you shouldn't be above 80. But again, it's not, if we were to take a piece of a beam, a lot of construction sites around here, I bet you we will be in the 40s, maybe even in the upper 40s with respect to the initial yield strength. And it's perfectly acceptable with respect to the specification, but it's not exactly defined. If you wanted to know, you can ask for the mill certificate associated with the exact beam batch that was produced for you. And if you do that, depending on the mill, some mill certificate will only give you chemistry, but most of them will also give you mechanical properties. And from there, you could say, okay, well, this was the requirement, and then you have what you got. So if you're trying to do a detail analysis, like find an element, trying to figure out when is this thing going to start to bend, buckle, and what have you, what you should put on are the actual properties, as opposed to the specification, because the specification are very broad. And it's a problem that you always face in design. In design, you could say, okay, I'm going to put this, so at least I know I have that. But what is the upper end of it is not as controlled if all you do is an ASTM. And that's why, just to tie back, because in the last lecture I mentioned about the aerospace specifications. If you have an aerospace specification, it will tell you a lot about how things needs to be done to a point that your properties are not going to vary anymore between 58 and 80. The range is going to be a lot narrower. Therefore, a number of reasons. One is, it's very critical, and the overall factor of safety is reduced. You can't fly something that's twice as heavy as it should be. And therefore, you need to account for all the variations in a more controlled manner. So really, in terms of basic ASTM, that 836 tells you you need a certain chemistry, and I avoided that part. No, not that. It's the table 2 on page 3 of your handout. Talks about some manganese requirement, but not for everything, only for plates. So if you look essentially at the manganese percent for shapes, which would be an I-beam, it says you can have as much manganese as you want. But then there's a note at the bottom, tells you up to 1.35%. And I think we can all agree that there's a lot of flexibility here, given how precisely we can control the properties of steel. This spec almost allows you to do everything. If you have impurities, as long as you extract the phosphorus, the sulfur, you control the silicon. Copper could be a problem with recycled steel. If you control these elements, and you're in the range of mechanical properties that is required, you got structural steel. Now, let's move on to a slightly enhanced version of this. I picked ASTM 572. One of the reasons is I've seen it used quite a bit on projects, structural projects that were not Walmarts, more the building enclosures for nuclear reactors or waste treatment facilities, where they have to design for seismic. They want a better understanding of what's going to be the steel properties. It doesn't mean you cannot use this steel for making a Walmart, but it does come at a slight premium. Good.
There you go.
It's actually on time for my images there.
Perfect.
Appreciate it.
Not a problem. And what days do you lecture?
We lecture every day, and I normally have my own plug.
Oh, okay.
I do wish that there will be one, because all it needs is this little, link about this long that has HDMI on one end and has the VGA. But I'll buy 3-4 more of those.
Okay,
Make sure.
cool. Thanks.
Are you gonna come pick it up?
Yes, we'll come get it when you're done.
Thank you.
Not a problem.
So the advantage of having a slightly higher specification is from one batch to the other, there's less variation. So here, they actually have different types, and that's the first table I'm showing on table 3. You have different types of that same ASTM 552 alloy. So it's type 1, type 2, type 3. As you go down the road, say we take a type 5. Type 5 tells us maximum 0.06% vanadium. It's very low. But they still call it vanadium steel because it does provide strengthening, I would say with limited consequences. So if we go there, all right. When I say ASTM 8572, it could come in all these types, 1, 2, 3, 5. If I don't say what I want, somebody else is gonna pick it for me. It always the case with these material specifications, so keep that in mind. And I was saying, well, if I go to a type 5, I just happen to know quite a bit what I'm looking for, because it's gonna be between 0 and 0.06, 0.80. Maybe that's what I want. Maybe it's not available. I'm gonna have to go back to that chart and figure out what they can actually sell me and use. The other aspects here on table 4, you see different grades. When we had 36, that was our minimum for the A36 steel. Now we have options. Our yield strength can start at 42 up to 65 KSI. And fortunately or unfortunately, we lost a maximum on the tensile strength, so these are all minimum. So if I take a grade 65, the minimum yield is 65, it can be anything higher than that. The minimum tensile strength is 80, or anything higher than that. One of the reasons for, at this point, not putting a maximum is if you want to be able to get these minimum elongations with this chemistry, you can't go too high in terms of cold drawing and cold working the material. So your material can't be fully cold work, because otherwise you won't have enough strain hardening to get this elongation and break. So it's self-control, but in general term, we call these performance-based spec, because I can go to the mill and pick my temperature, pick my drawing ratios, my rolling ratios. As long as I have the chemistry and I meet these mechanical requirements, I don't have big anomalies. There are, the ASTM specs are 10 pages, and they call for other specifications in terms of basic requirements, how you're supposed to measure stuff, how you come up with these properties here. If you saw that dog bone sample, that's part of this. This is not something I machine a sample the way I wanted. I get the number, I say, oh, it meets ASTM. I need to run the test the way ASTM wants me to run it for that specific shape. So there's one ASTM spec for testing steel products. If it's a wire, it's different than a plate. It's different than a sheet. The duck bone there is very typical for sheet products. So all you need to do is cut it out. You use the overall thickness and you run it. If you've seen that it was machined a little bit, there was an alkali treatment on it, so there was a little bit extra protective layer for that specific piece of aluminum I was testing. And the spec tells you to test it with the extra anodizing. But I didn't want my properties to be lowered, even though I knew that the aluminum properties were actually higher. That's why I took it off. So I don't meet, when I ran that test, I didn't meet the STM specification. I did it my way. So I wouldn't be able to say whether my sample I had met or not the STM specification. So it's really not complicated. At the same time, I could say the first year I was exposed to this, I kept learning. Because you think you got it, like you think you figured out how it works, and then someone comes in and say, oh, we got this steel here on the MBTA and would like to weld it. Okay, tell me a little bit more about that steel. Well, it was put in here, we think about 60 years ago. Oh, okay. So you have to go through that process of determining, are we going to be able to weld this? The first thing I would always ask is a chemical analysis. Because otherwise it could be anything. It could be high-strength steel that you can't weld. So this idea of getting at least one number of the chemistry was typically, the way I was treating this, I was going back to the ASTM here. And I was able to say, okay, for the shape I have, do I meet the sulfur, phosphorus, manganese, and silicon requirement? And if I did, I loved having some indication that my material properties were okay. But that's not easy. If it's a structure that's being used, taking a coupon out for testing, you have to explain yourself a lot. So a lot of times, what ended up happening is I was building a case that because the chemistry was right, and it was at an age where the control for manufacturing steel was fairly consistent, that we could just assume that it was the most basic structural steel and weld it accordingly, according to regular welding procedure. And as a safety precaution, we always had more non-destructive testing after the fact. So if there was any problem of picking up of hydrogen or anything during the welding process, getting some little cold crack under the surface, by ultrasonic testing, we were able to point that out after the fact. But it's useful to have the specification and history, because this was done a long time ago. There's been a lot of welding done on material with only this level of specification, and it works. So if you have it, you should be able to weld it as well. So it works both ways, even though it's a little hard sometimes to find what you're looking for. When you do find it, you can use it. Now, you can use it, but the properties you get out of welding this steel are the lowest. And I never really tried to take a steel that I didn't have a mechanical sample to say, oh, no, this is not grade 36, this is grade 50. You know, I would need to have the data to boost it up. But to say, okay, we're going to take it as A36, if it has all the chemistry requirements, was something that I've done day in and day out. Yeah, we covered this. So the basic spec for material, obviously, is chemistry. In steel, you have to worry about impurities. In aluminum alloy, depending what you're looking for, if you're looking for electrical conductivity, you want extra pure. Otherwise, a lot of times you're looking to put alloying element to increase your properties, because aluminum is so soft. But the second step that the ASTM allows us a very nice framework. That's what we were talking about, for how you're going to, what are the requirements and how you're going to test it. It does have some limitation in terms of how exactly is going to be the material produced. If you roll it, if you cold work it, it just doesn't make a difference. And I'm going to show you an example here that is more specific. These are SAE bolts. It's kind of, I would consider that one step up. If you ever heard of grade 5, I think if you go to McMaster, you can buy grade 5 bolts, grade 8 bolts. They come from that, a lot of them come from that SAE spec. If you look here at the chemical requirements for different grades, this is very, very basic bolts. Don't even consider, you guys will not specify what you want if that's what you specify. You just get a utility bolt. And then grade 5 is fairly common. It does say quench and temper. Oh, that's interesting. And then grade 8 is very common if you're going to have repeated loads on a connection. We'll see later, one of the differences is the minimum yield strength that's required. But if you look at the chemistry, they're very much the same. There's a little difference here of a lower phosphorus and a lower sulfur content, but the main difference, as you'll find, is in the heat treatment. So in that spec, there's this little paragraph on the heat treatment. I'm sorry if it's not perfect quality, but it's a copy I've been using for a while. So. It talks about, okay, you may need to do a stress relief if you have a kind of a general grade fastener. If you cold form the head, I don't know how many of you know this, but a lot of times the way you make a bolt is you start with a rod and you press, you forge the head, and it can be done cold with some consequences. If you really do it cold, you have a lot of residual stresses. You deform the steel in a way when you let it go, it springs back and you have areas of compression and area of tension. Now, if this was to go in a chemical environment where stress corrosion cracking will take place and other things will take place, it can happen underground, it can happen in a factory, you could start forming crack just from the residual stresses. So here, they say, if you have this grade of bolt, a grade 2 bolt, it's going to be stress relief, so it avoids that problem of residual stresses. Now, if you keep going up, talks about quenching and tempering, and it will tell you temperatures. If you go to here, grade 7 and grade bolts and screws shall be heat treated or quenched. So they tell you how you're going to quench it and temper to a minimum temperature of 800 Fahrenheit. Then it keeps going. So this is how you get your consistency and your higher performance, because you're being very specific about what you want. It's implied, that's a part that I'm not too excited about, but it's implied in this specification that you will form the bolt and then finish your heat treatment after that. And one of the reasons is you get the best in terms of your surface properties. And one of the consequences, every once in a while there'll be someone buying a bar that's being quenched and tempered to the same requirement and machine treads on it, and you don't get the same properties than if you did it the other way around in terms of getting to shape and then doing the heat treatment. So there's a lot that is either specified or not specified in the specifications of material and process, because again, now we really hit more of the process detail with those bolts. Now, why are they doing this? Fasteners are prone to fatigue failures. You have all these treads. You have all these treads, so if you start, a lot of times the way we're going to do the analysis, say, okay, it started, you have the shank here, where it's not threaded, and then you have the bolt head. See? If I start a nominal 1 inch, it gives me a certain nominal stress through here, and then I have what we call a net stress here when I consider just the going all around on the root of the threads. That's already a knockdown factor of 30% sometimes. So that's the difference between gross or nominal stress level to the net or effective tensile stress level. But after that, so say we're doing a grade 8 bolt, and it's telling us we have 150 KSI of tensile strength minimum. When you get to the net area here, it will be the equivalent, and I'm going to throw approximate number here, of say 120, because it's net. Now, if I consider all the stress riser associated with a root like this, even if it's just pure tension, going back and forth, I'm likely to have to knock this down by about a factor of 5. So if I started really high in strength, down the road, when I divide by 5, I'm getting into, 20, 25 KSI range. And even though I'm doing it very rough for you guys, 28 KSI is the approximate stress amplitude that these bolts will take, even though they have 150 KSI of yield strength. Now, if if you reduce the yield strain, I said 150, if you reduce it, it will reduce that 10 KSI to 18 or 13 or whatever it is. So you still care about the initial yield strain because that's what prevents you from initiating cracks. If you have seen that part of material strength. But you're not getting exactly what you could think you're getting when you're looking at these tables. One way to avoid this issue is to preload the bolts. Most bolts, it's going to be a flange connection, so we're looking here, the most difficult connection. I have the bolt going through the thread and rod. I'm only going to do one. Put a nut on each side. Then I got two big flanges. So we're cutting through here the assembly. So these are two flanges. We got one bolt, and it's got a nut on each end, so we see the thread right here. If I want this assembly to be resistant to any cyclic load, this happens in pipe connections, for example. If you have a water line, there's always going to be variation when valves open and close, and if seasonal variation from ground settlement going up and down, or if it's a big pipe, and you're going to want to avoid having these variation into the bolt. So what you do is you tighten it up, and when it's a whole assembly, it's a little bit like a compliant spring into a much softer spring. A harder spring. The hard spring is this flange against the other flange. There's a lot